All right, hi there to everybody watching the recording. I did want to start with some business today. As you may know, next Monday, a week from today, is Memorial Day, so we won't be having class. But in order to sort of make up for that missed class, here's what we're going to do. Today, I'm going to try to get through all of Chapter 11 as much as I can. And then we're actually going to jump into Chapter 12 this Wednesday, the first part of it. We'll do the second part of Chapter 12 next week, next Wednesday. So you're only going to have your homework for Chapter 11 due this week. So you don't have to worry about doing any homework on Chapter 12. But I just wanted to let you know we're going to sort of try to blow through as much as we can of Chapter 11 today. And then we'll switch over to Chapter 12 on Wednesday, which will then continue next week. And the homework for Chapter 12 will be due next week rather than this week. Is everybody good on that? Any questions? Just trying to take Memorial Day into account here. Usually it works out perfectly where it's in week 9 and we just spend one day on Chapter 11 and it's fine. But yeah, unfortunately it fell into week 10 this year. So there you go. Okay, so in that case, let's jump into Chapter 11. So I'll start out with 11.1, which is not much that we need to talk about because most of it you probably already know or we've already talked about in this course. A power function is a function of the form f of x equals x to the n, right? Where x is being raised to some power. It's called a power function. Okay. I also mentioned a floor function, which is denoted like this. And just for a little practice here, right? If f of x is the floor function, what's the floor of 5? Five. Okay, what's the floor of 5.2? 5. What's the floor of 5.999? 5, right? So the floor means take the decimal, if it exists, and get rid of it, right? And just leave the whole number part in the front, right? So it's rounding down. It's rounding where you always round down. That's the floor, right? And I should mention the ceiling as well. So the ceiling looks like this, right? So what's the ceiling of 5? 5, good. Ceiling of 5.2? 6, good. And the ceiling of 5.999? Also 6, good. Okay, cool. So, So the floor is rounding down, the ceiling is rounding up. That's why they're called that. Because the ceiling's beneath your feet and the ceiling's above your head. So we can also talk about multiples of functions, which is called a scalar multiple, right? Where if you had, f of x equals some coefficient, I think they called it m in your book for multiple, so I'll use m times x, right? What that means is that you just multiply this number by that, and that's your function, right? Which is pretty straightforward, I think. Algebra 1 type stuff. Any questions about any of these functions that we've discussed? Power function, this is called what do we call it here? Multiple of a function. Oh, and they did do this in the book, so I guess I should say that. There's a new notation where they put an m in the front, right? So they said, oh, well, that's a multiple of a function where you're just, multiplying whatever the contents of the function is. I put an x there, but I think I could have had a multiple of, it could have had x squared or some other function in here. And it's all that it means is you're just multiplying it by a coefficient, right? Okay. So any questions on all those functions? Does that sound okay? Good. Okay, cool. So in that case, let's talk about increasing and decreasing functions. Okay. And they don't have to always be increasing or decreasing, but we say that they're increasing in a particular interval, right? Or over a particular set. And an interval is just a set, right? So we would say f of x is increasing on a set S if and only if what exactly? I'm happy to have an English explanation, formal logic, algebraic, however you want to talk about it. So what are your thoughts on this? You could define it in terms of derivatives, but we're not going to. You absolutely could, right? So, okay. So that's really interesting, Nathan and David. You guys said some really fascinating things there. So do those mean the same thing? If x1 is less than x2, then f of x1 is less than f of x2, right? And then David said if x1 is greater than x2, then f of x1 is greater than f of x2. Nathan and David, is what you guys said the same, or are those saying two different things? Nathan, you think they're the same? David, you said yours is decreasing. Not quite. Not quite. Yeah, yours is not decreasing, David. It almost is. There's one thing flipped. So let's go with Nathan's first then. So Nathan said if x1 is less than x2, then f of x1 is less than f of x2. Right? Okay. So let's pause there. Sorry, I should have said for all x in S. So sorry, this should have gone at the beginning, pardon me. For all x in S. Right, because it's only on this set S, right? So let's try to interpret that visually or graphically. What does this mean if one x is less than another, then the function that at that x is less than the function at the second one? Bigger y for bigger x. That's a good way of putting it, right? Okay, and what does that mean graphically? So I think, David, that's a great English description. What about a graphical description? Let me start with a graph. How about that? Positive slope. That's a great way of putting it, right? So here's my graph, x and y, right? And I have this set. I'll make this a little bigger here. I have this set here called S, which is some set of real numbers. I guess I should have put set of real numbers contained in the reals. Not an element of, contained in. There we go. Contained in the reals. So there's my set S. And this is saying positive slope. It doesn't have to be a constant positive slope. It can be curvy, right? But the thing is, it's always going up, right? That's why it's called increasing. It's going up, right? Now, why is that? Why is it that this means it's going upward? So maybe let's break it into parts, right? Or if you're already typing, feel free to continue or hop on the mic if you like. But this is saying x1 is less than x2, right? So these are the inputs to our function in a second here, right? So x1 and x2, those are just points on the x-axis, right? So there's x1 and x2. I should have made my picture here. I'm just going to make a bigger picture that we can see easier. There we go. There's S, there's X and Y. I'll just do the, we could go into all four quadrants, doesn't really matter. Here's X1, here's X2, right? And here's our function on S. Okay. And we're saying X1 is less than X2, right? So within our set S, so here's our boundaries on S. Maybe I'll just like, there we go. So there's S, right? Some interval. X1 is less than X2. So X1 is to the left of X2, means that f of X1, which is the Y value corresponding to it, there's f of X1, right, is less than f of X2. Does that make sense? You see how that makes it increase with this, this description here, right? Because as the x's move farther to the right, the y values of those x's have to be getting bigger and bigger, right? People happy with that? Questions? Okay, so let's try decreasing, right? So here's increasing. So f of x is decreasing, and let me not screw it up this time. Decreasing on a set S, which is contained in the real numbers, if and only if, for all x in S, what? Let's see if you guys can get this part. Good, right? Same first part. X1 is still less than X2, but that implies that f of X1 is greater than f of X2. Nice, Nathan. Greater than or equal to, let's see, are they? No, they actually do a strict inequality here. Oh, I'm sorry, that's not equals, that was the arrow. Okay, so your equals is not less than or equal to. Pardon me, I just misread it. Okay, so what we've got here is what kind of slope in that case? negative slope, right? So for the region of S, however big it is, we've got some kind of negative slope there, right? And so between x1 and x2, what have we got? Well, here we've got x1, and this is f of x1. We've got x2, and that's f of x2. And as the x's get bigger, the function of those x's gets smaller, right? Because now the function to the left, the function on x1, which is the item to the left, is going to be bigger than the function of x2, which is the one on the right. Yeah? What do you guys think? Questions? Okay, so at this point, we've got all the machinery we need to talk about big omega, big O, and big theta. Okay, so these ideas were developed by Don Knuth back in what, the 70s, maybe 60s, I forget, somewhere in there. Yeah, it doesn't say. It says when they were invented by Paul Bachmann in 1894, but really Knuth popularized these guys. This is Don Knuth. Make sure I spell it right. Knuth. Yeah, no, that you say the N, or you say the K. Pardon me. You always say the N. You also say the K. Yeah, you really do. Yeah, it's not Knuth. It's Knuth. Yep. Yeah, it's weird. And so this is from like the 1960s, thereabouts, somewhere in there. And what you're going to do is you're going to talk about how functions get bigger, okay? And in particular, how fast they get bigger. But it's not like a derivative where you're taking a precise measurement of how fast the function gets bigger. Mid-70s. Thank you, David. Yeah, so this is in the 1970s. So you're not talking about precisely how fast it gets bigger, like what you would do with a derivative. Instead, you're just putting some limitations on how fast it could get bigger, right? Or how slow it could get bigger, depending on which way you go. And so you're not saying precisely what it is, you're just giving some boundaries. And you're saying, hey, well, I know this function's getting bigger, but it's never going to get bigger that fast, and then say how fast that is, right? Or, I know this function is getting bigger, but it's never going to get bigger this slowly, and then describe how slowly that is, right? So here's the idea. We're going to have, and this is called, we'll just call this big O. Generally, people only talk about big O notation, mid-1970s. So usually people only talk about big O notation, which is an upper bound, okay? Big omega is a lower bound and big theta is both. Now, let me ask you a sort of a leading question. Why would computer scientists be so much more concerned with an upper bound than a lower bound? Like what's sort of the point of an upper bound? Oh yeah, and so David, let me answer your question. Yeah, so the big O is from Paul Bachmann, but it was popularized and made useful for computer science by Knuth in the 70s. So yeah, so it was originally invented by this guy Bachmann, but really it came into fashion by Don Knuth, who was using the work of Bachmann, some 80 years later. Yeah, it was popularized for computer science at that point. Yeah, and Nathan, that's right. So and Lucas, that's on the right track too. So the reason why computer scientists mainly are concerned with big O, which is an upper bound, is we want to know the worst possible thing that could happen, right? As computer scientists, we're always worried about Murphy's law, And does everyone know Murphy's Law? You know what that is? It's not a real law. Well, it's a real law, but it's a real goofy law. If something can go wrong, it will. Perfect, right? The worst possible thing will always happen, right? That's Murphy's Law. And as computer scientists, that's how we approach programming is we think, okay, well, we have end users that use our programs, right? And we assume that these end users will do the stupidest possible thing every time and ruin all the hard work that we've done without fail, right? And we go into making in a program with that assumption, right? And that's why big O notation is so important, because an upper bound puts a limit on how bad it can get, right? Like even if the worst possible thing happens, this is the worst that it could possibly be. This is as bad as it could possibly get, and it won't get any worse than that. We can mathematically guarantee that it won't get any worse than this, right? And sometimes, sometimes computer scientists are interested in big omega, for example, which is the best case scenario. We'll say, well, okay, well, in the best case scenario, it can't get any better than this. But that's not usually what we're talking about, right? Usually we're talking about the worst case scenario, not the best case scenario, right? So let's define big O and big theta and big omega as well. So we're going to have f and g be real valued functions on a set of non-negative real numbers. Okay, so that means that f is a function on non-negative real numbers, which could be, I guess the outputs, I guess we're saying all the outputs are going to be, the outputs have to be positive? I don't think it says. It just says that the inputs are non-negative. Yeah. So positive reals to the reals. And g is the same thing, just another function from the positive reals to the reals. I'm going to go ahead and say positive reals. I don't think we need to worry about negatives here. So everything that's happening here is going to be happening in the first quadrant, right? Now, what we're going to do is we're going to compare f and g, okay? So our first one, f is omega, that's an omega, right? Of g, we could say g of x. Yeah, we'll say g of x, that's fine. If and only if there exists a positive real number a, there exists a in the reals, and a little a in the reals. So, oof, I already screwed up. Uh-oh. Let's do this. Okay, so a big A and a little a, both in the real numbers, such that oh boy, I'm really ruining this. Okay, I'm gonna try again. Let's do this better. Okay, there exists a little a and a big A in the positive reals. Your book is totally destroying the right order for the quantifiers here, so that's why I did it wrong. I'm trying to fix it. So for all x greater than little a, there we go, a times the absolute value of g of x is less than or equal to f of x. Absolute value of f of x. There we go. Perfect. Okay. I guess I should just do the rest of them, and then we'll discuss. So let me just finish writing these out, and then we'll talk about it. Okay. F is big O of g of x, if and only if again, there exists a little and big A in the positive reals, such that for all x greater than little a, it goes the other way. Your book uses b's here, but I don't care about that. So f of x, absolute value of f of x, is less than or equal to capital A of absolute value of g of x. Okay. And finally, we have big theta. Okay. F is theta of g of x, if and only if. All right, now here's where we need A and B and K. So that needs a plus on it. Okay, so great. So we have there exists K, A, and B in the positive reals, such that for all x greater than K, A times the absolute value of g of x is less than or equal to the absolute value of f of x is less than or equal to the b times the absolute value of g of x. Cool. Okay. So let's go through and explain what the heck is going on. And I think it might be easiest actually to start with big O, because that's what we were talking about before. Big O notation is meant to think about the worst case scenario of what could happen. So let's trot through a little example here. And I think your book is going to have a really nice description here, graphical description. So let me pop over to here. Zoom in on that guy. Bloop. And they have a B here. Here, let me make it an A. All right, cool. So here's what's going on. This is A times the absolute value of G. Okay, so this black line is the function G. Okay, the blue line is the function F. Okay, and what we're saying is F is big O of G. Okay, and what that's saying is F is bounded above, F is at most G, right? So bounded above and at most, those mean the same thing. There's a boundary on top of it, right? So remember, F is the blue one, G is the black one, right? So it's saying, okay, well, what happens is I've got my graph F, which has this little bumps in it, okay? So we have these little bumps, and then it just sort of smoothly goes up like that. And we're saying, okay, well, this graph F here has a boundary of the black line above it, right? And that means that we have a worst case scenario for F, because the worst case scenario for F is G, right? Because G is going to be on top of F. It's going to be greater than F for the entire rest of F's life, all the way out to infinity out here, right? No matter what F does, G is always going to be on top of it. So the worst case scenario, and by worst case here, we mean the largest number that F could be, G is always going to be an even larger number than that. Okay, so let me ask you a question here. Why is it that the worst case would be a big number? Why is that? When are big numbers bad? Why would the worst case scenario be a big number? Yeah, if it's measuring time, right? That's exactly right, Amber. So if we're measuring time, The bigger the number, the worse off, right? Because if we are, waiting for an algorithm and we're measuring how long it takes, which is the whole point of this, right? Then a bigger number is bad because it's a bigger amount of time. You have to wait for it to finish and find your answer, right? So in this world, big numbers are bad, right? Sometimes big numbers are good, right? But if you think of, how many miles it takes to I don't know, to get to your birthday party, okay, um, then a big number is bad, right? But if you're talking about how many dollars are in your bank account, the big number is good, right? So we're more in the idea of you're trying to drive and you're wondering how many miles it's going to be, rather than you're trying to make money and you're wondering how many dollars are in your bank account. It's the former, not the latter, right? So are there questions so far? Does that make sense? We're trying to measure how long algorithms take. We're assuming that the user is going to do something terrible and ruin our program, and we're wondering what the worst possible thing is. We're measuring how long our algorithm takes in terms of time, right? And so a big number is bad and a small number is good because we want it to be done so we can get our answer. And we're saying that G, this black line, is always going to be on top of F, the blue line, so that we have a measurement of the worst case scenario for our algorithm. People good so far? Who's got questions? Okay, let me ask you a question. What's this little b all about? What's going on with that? Although in this case, I changed it to an A. My discussion there. Here, let me help actually. That. Okay, so there's my big O definition, right? I've got this little a thing going on here, and the capital A as well. Let's talk about both of the A's. So I have little a and big A. Here's my definition of big O right here. The point at which the relationship starts. Good, David. Can you say more about that? That's perfect. Can you describe a bit more? Like, what is this x greater than a thing going on here? Why does that mean the point at which the relationship starts? Good. Once x passes b or a, either one, then the function values of y will follow the inequality. Yeah, that's great. Perfect, right? So what we're doing is we're thinking about f of x versus g of x, which is what we're looking at with these two lines, right? What we want to say is, hey, f of x is going to be smaller than g of x, right? Well, but these x's here along the axis might not always have this relationship being true, okay? All that we're saying is that the relationship is true past some certain point, right? And that point where the relationship starts, as David correctly said, is the point little a, right? And you can see here, the blue line is on top of the black line before that point, right? Before a, the blue line is on top, right? But after a, forever, all the way out to infinity, right? From then on, the black line is always going to be on top of the blue line, right? So we're saying there exists some point such that for all x's past that point, all x's greater than a, so past that point going toward the right, the function f is going to be less than the function g. So the blue line is going to be underneath the black line. Does that make sense? People happy with that? Questions? Okay, so what about the big A? What's going on with that? So with this big A situation there, and there, and there, what's that all about? Yeah, multiples of a function. Yeah, exactly. Yeah, a coefficient times that function. Nice. Okay. So so you're right that we are talking about multiples of a function, which are coefficients. And what exactly is it saying? Like, what does this mean? That there exists a big A, which we then get to multiply by the G function. Like, what does that mean?
Sorry, I think this would take a little too long to try and type
Yeah,
out.
yeah,
So
please.
that coefficient A, it could be any number. It could be bigger than one, less than one, whatever. It's saying that like g of x is like the shape of the function, and the coefficient is like a scale factor. So you can scale the shape of the function such that it's always above or below whatever function you're talking about
Good,
with a scale factor without changing the shape of it.
good. You can pick whatever A you want. All that we're saying is that it exists. There are no limitations on it other than that it's positive, right? But we're saying, okay, there's some sort of coefficient, right? Where if you multiply G by that coefficient, it'll be bigger than F. Let me ask you a tricky question. If we can pick any A that we want, can't we always make G bigger than F? Why don't we just pick A to be a million or a trillion or however big we need it to be in order to make G bigger than F? Right? Wouldn't our ability to pick any A that we want render this whole idea useless? And no, good, no. Why not? Because it says for all x bigger than A. So we could choose an insanely big x, which then renders the insanely big A. We make even an insaner big x to render that really big A then useless. I think an example is going to be helpful here, right? So what if I say, I want my big A to be a million, right? And let's talk about, let's say that we want our, I'll make a little picture here. So let's say that we have, A is equal to a million. So we have a really steep line here. This is not to scale because that's only a slope of like 3, but you get the idea, right? So here's f of x, yeah, f of x equals 1 million x. A million times x. So it's a linear function. Sorry, it looks kind of curvy. Sorry about that. I meant to draw a line here. This is just a line, right? But what if we have g of x equal to x squared? Right? Now, if g of x is x squared, well, obviously this is a bigger function than this one in the sense that the exponent is bigger, right? So what's going to happen in this case? Well, g of x is still going to be, sorry, I did it backward. Uh-oh. Here, sorry, let me switch it. That's supposed to be G. This one will be F. There we go. Okay. So why does this not work? Sorry, I did it backward. So the A is supposed to be multiplied by the G function here. So we have A times G of X. This is the second one. We're talking about big O, right? Yeah, because F is going to be way bigger than G not way bigger, sorry, they'll be equal. No, David, you got the crossover point, so that was perfect. They'll be equal at 1,000,000, right? If x equals 1,000,000, what's g going to be? It will be 1,000,000 times 1,000,000, right? Because we got the million coefficient and x is 1,000,000. Well, what happens at f? Well, it's the same thing. It's 1,000,000 squared, so they're equal, right? So what happens is we have this situation where it starts off less, and then it crosses right here, and there's a crossover point, right? And sorry, I kind of tipped it back the other way, which is totally wrong. I'm sorry, my drawing's not great today. But what's happening is you're trying to say, okay, well, I want to have g be the function on top, right? So because remember, g is the black line here, right? And then f is the blue line. So we want g to be on top, the worst case scenario, that is an upper bound on f. And here, that's not working, right? Even though we have this huge number of 1,000,000 on g, right? It's still not going to be an upper bound on f for all x greater than a. Because what if a right here is 1,000,000? Well, at that point, g is not going to be on top of f anymore, right? F is actually going to get bigger and bigger than g, which is the opposite of what we're going for, right? So what really is happening here is a study of asymptotics, right? So maybe someone should define that. What does asymptotic mean? I'll spell it out for you while you answer. Comes from the word asymptote, which maybe you've heard of.
So there's two kinds of asymptotes.
Okay.
And the one you've drawn there is a vertical asymptote. So basically, like as it approaches that value, it's going to like almost become a vertical line. I mean, I don't know exactly what function you drew there. It looks like a squared function, so it's not
Yeah,
actually going to be a vertical line.
It's a bad drawing. This is supposed to be x squared, and this is supposed to be 1,000,000 times x.
Sure. So
So
eventually, x squared will get so much bigger than that.
right. And actually, because my drawing was bad, I think I confused you. It's actually not a horizontal asymptote. It's not a vertical asymptote that we're talking about. It's a horizontal asymptote. But I think I confused with my drawing because my drawing was terrible. So let me back up a second. There are two kinds of asymptotes. There's vertical and horizontal, right? And the word asymptote, well, we didn't even get that. So what does the word asymptote mean? Let's start there. If we're talking about asymptotic behavior, what does that mean? As something approaches infinity, that's right. So asymptotic, all that means is going toward infinity, right? Like Star Trek, to infinity and beyond, right? That's what asymptotic means. So what's happening here is we're saying, okay, we're talking about all of the x's bigger than a, right? Where, these x's are real numbers, okay? So these x's can get infinitely big, right? They go out toward infinity, right? So 1,000,000 is not very big, right? Because we're talking about all the x's, a billion, a trillion, a quadrillion, all of them, all the way out to infinity, right? And what's happening is if you allow the x's to have asymptotic behavior in the horizontal direction, right? The x's are going out this way, along the x-axis here, right? Well, eventually, what's going to happen on the x-axis is that even though you have a giant coefficient on g, f is still going to overcome it eventually, right? It might be a billion numbers out, but eventually the x squared function is going to get bigger than any linear function you choose, no matter what the coefficient is. Linear being x to the first power, right? So I could choose 1,000,000, I could choose a billion, a trillion, doesn't matter. If I only have a linear function here and I'm comparing it to x squared, eventually at some little a, they're going to cross. because x squared gets bigger faster than the g function does, no matter what coefficient we put in front. And that really is the whole point of this thing, right? Is saying when we have functions and we compare how fast they grow, it doesn't matter what the coefficient is if we let these functions go out to infinity, because eventually the one with the higher power, right, the one with the squared instead of the x to the first, is going to get bigger eventually, right? People happy with that? Does that, people have that intuition? Does that make sense? Or people have questions or problems? Okay, feel free to jump in if you got some questions. So what we're saying here then, with the big O notation, is that we're picking some little a and a big A, such that for the asymptotic behavior of the functions, for all x bigger than little a, past some certain point, the function f has an upper bound, right? Has this function g on top of it times some coefficient, right? And really what that's getting at is that the coefficient on f doesn't matter, okay? Really what we're doing is when we're talking about these functions, we're saying any coefficient times the function, we just don't care about it, right? And the reason why is because when we pick our upper bound, we can pick whatever coefficient we want, right? There exists some capital A, so we get to pick it, right? And that's saying, okay, well, as f gets bigger, maybe f has a really big coefficient. Let me do another example, right? So let's say that I have, f of x equals, we were talking about 3x squared earlier, right? So I have some picture, my function goes like this, where f of x equals 3x squared. Okay. Now what I'm saying here is that when I have some function g of x, I can pick whatever coefficient I want, right? So if I say g of x is just a regular old x squared, well, if I did that, it wouldn't work, right? Here's g of x equals x squared. That wouldn't work. Now, f of x is on top of g of x, and I haven't accomplished what I was trying to do. But in my definition here, it says, okay, but for this g of x, I get to multiply by any big A that I want, any coefficient that I want. So really what I want to do here is I'm going to say, okay, well, here's my new for, g of x. Well, yeah, I'll just say for g, right? Where 4 of g equals 4x squared, right? And now because I could pick that 4, I can easily pick a coefficient that's bigger than 3. And that has the effect of rendering any coefficient that I put on f pointless, because I can just pick a coefficient on g that's bigger than it, right? So really what we're getting at here is that the coefficients in front of the functions that we're trying to put boundaries on are not relevant. We just don't care about them. Okay. Why? Why would we not care about the coefficients on a function in computer science when we're measuring how long algorithms take? Why would it be that we just throw coefficients in the trash and they don't matter? Any ideas? Okay, the growth rate depends on the shape of the function, not its scale factor. Yeah, and I would say negligible is really the important word there. I think that's the really the key point, right? because the coefficient on a function doesn't matter if we're talking about functions with big exponents, right? If I'm talking about, x cubed, for example, it's not even that big of a power, it's only cubed, right? And I'm talking about x cubed, and I'm wondering, okay, I have this algorithm that's an x cubed algorithm, okay? It takes, the amount of time that it takes the algorithm to complete is the size of the input cubed is going to give us the amount of time involved, right? Well, what if I want to run this algorithm on, on some data set that has 1,000 entries, okay? Well, 1,000 cubed is already a billion, right? Does it matter if it's 2 billion or 3 billion or 1 billion, right? If if I have to wait a billion seconds for my algorithm to finish, does it matter if it's 1 billion seconds or 2 billion seconds or 3 billion seconds? Well, okay, so Lucas, I'm glad you're taking up devil's advocate, okay? Waiting a day versus waiting 3 days is a big difference. Maybe, but maybe not. Why would that not be a big difference? What kind of algorithm would you not care if it took either 1 day or 3 days to finish? Not sure. Okay. So you're absolutely right, Lucas. You're playing devil's advocate exactly the right way. So what do you guys think? Why would it not matter 1 day versus 3 days to wait? What kind of an algorithm would that not matter for? Okay, if you have a deadline far in the future, it wouldn't matter, right? So if you had a year to finish and you can either finish in 1 day or 3 days, doesn't matter. Okay, that's true, but that's actually and you're right. It's funny. That's actually the exact opposite of the way I was trying to argue. Although you are right. So what's sort of the opposite of that idea? Yeah, you need it immediately. And that's much more common, right? Because when you're designing an algorithm, usually you're not expecting that the people using your algorithm have a year for it to finish, right? How fast do people want the answer from their computer? When instantaneously, right? Here's an example of an algorithm where waiting a day versus waiting 3 days doesn't matter. You're trying to load a web page on your phone. Perfect example, right? If you're trying to load a web page on your phone, do you care if it takes 1 day versus 3 days? What happens if 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 you go to the app store and your new web browser says, "Hey, our app only takes 1.5 days to download a web page." What do you do? Go to the next one, right? Go find someone else's algorithm, right? If I have to sit and wait for a web page for more than 5 seconds on my phone, I turn off my phone and I don't care anymore because it wasn't that important in the first place, right? If I'm trying to run some program on my computer and it gives me the little, spinning circle or the little hourglass, right? How long am I going to sit there and wait and stare at it? Depending on the program, but maybe 10 seconds before I close it and try again, assuming that something went wrong, right? It's got maybe 10 seconds for me. I have ADD, so it's, it's very, I'm only going to wait a very short amount of time. And most people now are like that, right? So uh, as David said, you could have a deadline that's far in the future, but most often your users are going to want an instantaneous result, right? And if you have to wait a minute, let alone a day or a billion days, right, or something like that, it's just a non-starter. It's just not going to happen, right? They've already, taken your app off of their phone and gone on to someone else's, or just decided they don't really care that much and go out and go out in the garden or do something else, right? Um, so really the reason why coefficients don't matter in this case is because a factor of 2 difference, or even a factor of 10 difference between the speed of your algorithm and someone else's doesn't really matter that much, right? Because if it's not instant, no one cares, right? No one's going to bother. Good. So Lucas, that's absolutely right. There are some situations in which the coefficients really do matter. And I'm glad you use frames per second, because that really is a good example of the category in which coefficients do matter, and that's hardware, right? In hardware, coefficients are vastly important. And people will say, my hardware goes 20% faster than your hardware, which is a huge difference, right? And that really does matter. For software, doesn't matter, right? Doesn't matter as much, right? It's not as big of an issue, right? And the reason why is because in software you can get these huge speed ups by changing the way that your algorithm works, but in hardware, generally those speed ups are not possible or available, right? And so people are, trying to pack more transistors on a chip, twice as many transistors on a chip, and you say, oh, this chip's way better, the next generation of chip, right? With twice as many of them on there, it goes twice as fast. Okay, great. And people are really excited and will pay a bunch of money for that, right? Or frame rate is another good example, right? But for software, it doesn't really work that way, right? Because people are impatient, I think is really sort of the thrust of that argument, right? Um, are people with me on that? Does that kind of make sense? It's not a perfect argument. Like Lucas, the spirit of where you're coming from is not, you're not wrong. Like you have a good point, but um, I think that people's impatience really does put some pretty severe limitations on software, where if you're saying, well, my software is twice as fast as yours, people don't really care, right? Say, okay, well, you know, I'll the amount of time that you need to wait in the first place is what matters, not if it's twice as fast or twice as slow, right? It's more like, oh, my software will give you the answer in 5 seconds, and your software takes an hour to do that same thing, right? That tends to be more of the distinction in software. And the reasons why are actually pretty interesting, right? It's because there's it's a good way of putting this. Because in software, there's a lot more opportunity for huge speed ups, whereas in hardware, there isn't, right? Like in software, if you're really clever in the way that you design an algorithm, then you can get a huge speed up on the thing, right? Whereas in hardware, that's not really something that happens very often, right? So I guess what I should say is software oftentimes has the opportunity for huge speedups where you can actually change the power on the function instead of the coefficient. Whereas with hardware, that doesn't usually happen. With hardware, usually these powers are fixed, right, by the hardware design and sort of just the evolution of computer hardware generally in over the last 50, 100 years, where so these powers are sort of fixed in hardware, and you're trying to optimize the coefficients. Whereas in software, you're writing a brand new algorithm that's just out of thin air that you just invented, right? And so when you do that, then there really is an opportunity to do your code differently, so that instead of it being x squared, you have a linear function. If you figure out a clever way to change that. change that algorithm. Does that make sense? Questions? Counter arguments? I'm always happy to have those. Okay, cool. So here's where we're at. We've got our definitions. Maybe I should label these. This is omega O and theta. Probably theta you know already from trigonometry, right? So we've talked about big O notation, which is saying the function f has an upper bound of the function g, picking whatever coefficient you want, past a certain point little a, okay? Omega is exactly the opposite. Here we're talking about the best case scenario. We're saying the function f has a lower bound of g, right? Which is the best case scenario for f. Now theta is saying both, right? So can someone give me an example of big theta notation? Some f and g where f is big theta of g. Can you give me example functions for f and g where that would be true? Yeah, linear, right? So f could be, 2x, right? And then f of x would be big theta of just g. So let me do an example here. Let me write it down, because if I say it aloud, we're all going to get confused. F of x equals 2x is big theta of g of x equals x. Why is that? Because of the coefficients, right? I can put a coefficient of 1, big A equals 1, and then this will be smaller than 2x, right, with a coefficient of 1 on there. Or for big B, I could put, 3 on there, say, okay, well, now, so what I'm going to get eventually is this is this, since A could be equal to 1 and B equals 3, right? And then what are we going to have? We're going to have 1 times g of x is less than f of x is less than 3 times g of x. Right? And by modifying that coefficient, a and b, I can change g of x to be either below or above f of x. Let me give you another example. Here, let me actually move this thing for a second. Okay. So let's do another one. So let's say f of x equals 3x squared plus 2x minus 10. Okay, so a nice quadratic function there. I would say f is theta of g of x equals what? X squared. Great. Let's see why. And for that, I'm going to actually not try to draw this, because that's going to be a disaster. Let me switch over to Desmos here. So here I've got, let's say my blue line is f of x. So I'll say 3x squared plus 2x minus 10. Okay, so here's my line. And here's my first g of x. G of x equals 1 times x squared. Okay, and then 4 times x squared. Let me zoom out. So you can see what happens here, right? So I've got my red line, that's going to be f. Blue is going to be my g function with a coefficient of 1. That's the lower bound. The green line is going to be my g function with a coefficient of 4. You can see that my blue line is a lower bound on f. The green line is an upper bound on f. Past this point right here, the crossover, right? And that would be my little a. Let me put it on this one here. Yep, there's my crossover point, right? So after 2, and if I go up to 2 up here, right? So after 2, the blue line is always going to be a lower bound on the red one. The green line is always going to be an upper bound on the red one, right? And so we would say that this function f here is g of x squared, because with my function g, I pick my capital A to be a 1, pick my capital B to be a 4, and in that way I can achieve a lower and upper bound on this function f simply by varying the value of the coefficient, multiplying g. What do you guys think? Questions? Okay, so what I want to say here is that you can have a big O or a big omega of different functions, okay? So obviously, you know, x cubed is going to be an upper bound on x squared, right? It's bigger, right? And, you know, x, x, f of x equals x is going to be a lower bound on x squared. And you can use functions to different powers for big O and for big omega, okay? But for big theta, you really have to have exactly the same exponent on there, because otherwise the lines will cross, right? You can't find coefficients big enough to compensate for a change in exponent, right? So if you want theta, right, where it's an upper bound and a lower bound, you really have to have exactly the same exponent here, or else it's not going to work. People okay with that? Questions? Okay. So, unless the exponent is greater for the function g of n. Well, that would work for big O notation, but that wouldn't work for big theta notation, because theta has to be able to be greater and able to be less. So you can't have a bigger exponent for the theta version, where you have to go above and below. You can't do a bigger exponent. It has to be exactly the same exponent, right? Exactly the same maximum exponent in your expression, which in this case is a 2. Makes sense. Okay, cool. Okay, other questions? Okay, so I realize this is complicated. We're going to take a short break. We'll take 10. Um, think about this for a minute. Go back and look through the definitions. See if you can figure out all the greater thans and less thans and coefficients and all that stuff. Okay, so you can come up with some questions. I'll take questions when we get back, and then we'll do a bunch of examples. We're going to do some examples just of functions and just compare them and see, is this one big O of this one? Is this one big theta of this one? Do some examples like that. Then we're going to actually go through some real algorithms and compute their big O values. And that's where we'll end it today. All right. Any other questions before we take a break? All right. Sounds good. Well, I'll see you in 10. Okay, cool. We could just do the rest of this. Oh, wait, yeah, we're recording. Good. Okay, so we can do the rest of this web work problem, or maybe let's move on to a new web work problem. Let's try the next one. Do a couple of examples from here. No, not that one. Let's do a Sorry, it's hard to scroll on my trackpad here. Okay, great. So let's do a couple of these, right? So we want to find the least integer n such that f of x is big O of x to the n for each of the following functions, right? So essentially what we're going to do here is we're going to look through the function, right? We're going to find the term with the largest exponent, and that's going to be almost the upper bound, right? But we want to find the least integer n. So for example, on this first one, what's the largest, the term with the largest exponent in part A? Yeah, so that it would be the second term, x to the 7 log x. This would be the term with the biggest exponent. And the smallest integer bigger than that would be 8, right? Because you can see x to the 7th times log of x, we can't get an upper bound of x to the 7th because we're multiplying by this log of x term, right? And so, this is going to be slightly more than x to the 7th because there's this other little increasing function of x that we've multiplied on. So x to the 8 would be the smallest upper bound on this function. What do you guys think? Questions? Okay, so let's try D, right? So on this one, now we have a rational function, not an irrational function, but a rational function, right? Where in the numerator, the biggest exponent is 3, and then the denominator, the biggest exponent is 4. So what do we do here? Yeah, so this is going to be x to the dominated by, or have an upper bound of x to the -1, right? So there's this other word that you can use to talk about upper bounds, which is dominated. And when a function dominates another one, that means it's an upper bound for it. No, that would not be its lower bound. That would be its upper bound. Well, it would actually be, well, so, right, because this would be, if we forget about, basically the whole idea here is just like deleting stuff. So let me do a little bit of explanation here. So basically, all that I'm keeping is the term with the largest exponent and throwing everything else in the trash, right? So that could be a coefficient like you have here, right? This 3 times x to the 7th, the 3 gets thrown in the trash, right? Any coefficient gets thrown away. Any term that has a smaller exponent, like log of x to the 4th, that goes in the trash. So this one, we're going to throw the 5 log x, that goes in the trash. The +1, that goes in the trash. We're left with x cubed over x 4th, which equals x to the -1st. And so that would be, David, you're right, actually, that would be big theta, not just big O. It would be an upper and a lower bound on f in this case. Does that answer your question, Sean? Okay, so if we weren't trying to find the least integer n, we could also say, you know, x to the 0 or x squared. Those are all upper bounds as well. A lower bound on this would be x to the -2. That would be a lower bound, right? 1 over x squared would be a lower bound on this, right? But if we want the least upper bound, that would be -1. Yeah, so 0 would be an upper bound, but it wouldn't be the least upper bound. Does that help? Yeah, cool. Okay, so let's see if we got 50% here. Hopefully we got 2 out of those 4. If it'll load. Oh boy. Oh, there. Oh, no. Thought it was going to work. Hey, everybody. Sorry about that. My internet died. Can you all hear me? Yes. Yep. Sorry about that. Had to do, but I think we're there. One moment here. I'm just getting set back up. Sorry about that. Right. Okay, cool. So we're back, we're recording. Okay, cool. Sorry about that, guys. So we were on problem 5. Here's what we had. We put in x to the 8th and x to the negative 1st. And let's check our answers here. 50%. Okay, so we did get the right answers on that problem. Okay, cool. So moving right along. Hopefully my internet won't die anymore. So what I wanted to do next is talk about analyzing some actual algorithms, right? And I have a variety of ones to talk about here. We'll sort of start with some simple ones and then get more complicated as we go. So, pin. Okay, so let's talk about some algorithms, right? So what we're going to do is we're going to go through a bunch of these guys and talk about their big O value. And what that means is their worst case scenario for how long the algorithm could take to finish, okay? In other words, what's an upper bound on the time that the algorithm takes as a function of how big of a sample we want the algorithm to work on. Let's start with a simple example. So we're going to start with sequential search. Okay, so sequential search. Okay, so what is sequential search, first of all? Let's talk about that. Feel free to put in the chat or hop on the mic, whatever you like. Step through a list, but one by one. Okay, in what kind of an order? So you said one by one, you're almost there. Can you be a little bit more specific? From start to finish. Okay, so one at a time from start to finish. And what are you doing as you step through the list? Okay, checking to see if we found a value. Okay, so we've got a list. We're looking for a value in that list, and we're wondering how many steps it's going to take. That's the run time. That's the amount of time that the algorithm will take is going to be, dependent on how many steps there are, right? What does that depend on, right? So in terms of, our function here, the output of our function is going to be, how long it took. What's the input going to be? Okay, so David, you said where the item is. That has an effect, but only on a specific run of the algorithm. In general, if we're talking about, doing lots of searches on a particular list, what attribute, what property of the list is going to determine how long it takes? And that's right, David, it'll be the size, right? The amount of items on our list. So we're going to have a function of the list size. And when we plug the size of the list into our function, that's going to give us the number of steps that the algorithm takes, which is, AKA how long it takes, the amount of time. Right, so then the number of steps that an algorithm takes is, the same idea as how long it takes, because there's a fixed amount of time for each step, right? So if we have sequential search, let's do a little example. So here's my list, right? So I've got a list, which is, 41826 943, and here's my search key is going to be, 6. right? So if my search key is 6, how many steps is it going to take till I find that value? More than 2. Yeah, 5, right? Because 6 is the 5th item on the list, right? I have to check this one. That's step 1. Check this one, step 2, step 3, step 4, step 5. So key of 6 leads to 5 steps, right? How about if I search for the number 3? How many steps is that going to take? 8 steps, right? And what about if I search for the number 4? How many steps is that going to take? Not 7. Yeah, 1, right? That's a tricky one because there's 2 4s on the list. And with sequential search, it'll reveal the first one before it gets to the second one. So 4 is just going to take 1 step. Okay. And so here's the question. What's the worst case scenario for how many steps this sequential search is going to take? The size of the list, right? The worst case is the size of the list, number of steps, right? And so what I'm looking at is this idea f of size equals size. So what kind of a function is this? Linear, right? This is the same thing as saying, f of x equals x. We got the same thing here, size, xx, right? So the way that we would describe sequential search is we would say, well, sequential search is big O of the size of the list, right? Or if you wanted to say it a little bit more mathematically, you could say, big O of n, right? Where n equals the number of items in your list, right? The size of the list. Or you say big O of size or big O of n, or, big O of f of x equals x. These all sort of mean the same thing. It's just different ways of saying the same idea, which is that it's linear, right? Any questions on that? Does that idea make sense? And hopefully you've seen that before. And people seen this before from like CS 161, something like that. Should be kind of familiar. Yeah, cool. Okay, so let's try a more complicated example. Going over it now. Okay, great. So let's do a more interesting one. Right? Let's do a binary search. And let's start off with an example. So in binary search, I'm going to have a sorted list, right? And so here's my list here. So my list could be 1, 2, 5, 7, 8, 13, 18, 21, 26, 29, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, cool. So there's my list. And let's say that my key, let's do a few examples here, right? So let's say that my key, and let's do the number of steps. Make a little function table here, right? So let's say that I'm looking for the number 5, which is on my list, right? So what are my steps going to look like here? And let me label these with their indices. Okay, so if I'm doing binary search on this list, searching for 5, what do I do first? How does binary search work? Okay, we're going to search 0 to 7. Okay, good. So how did you get there, Nathan? So let me do this step before your first step. So you're right, you want to search from 0 to 7, but how did you figure that out? Okay, 5 is less than 21. So what you're doing is you're looking halfway down the list, which is this guy, right? Is halfway down, and you're comparing your key against the item that's halfway across, right? And since 5 is less than 21, we're going to not search from 21 up through 50, right? So all of these numbers couldn't possibly be our key value because our key is less than 21 and everything over here is bigger than 21. So 5 couldn't possibly occur on the right-hand side of the list because it's smaller than the central value. Does that make sense? People have questions on that? This is, of course, relying on the fact that our list is sorted. If our list is not sorted, binary search doesn't work. It just fails, right? So you'd have to assume that you're starting with a sorted list, right? But if you are, then we can eliminate the whole right-hand side. Questions? Okay. So in that case, what happens next? So we compared 5 against 21. It was smaller than 21. Okay, the next step is we examine, Nathan, you indicated here, we would examine halfway down the remainder of the list that's still viable, which is all of the stuff to the left of 21. This is the viable section of our list that remains, right? And we search, we do a comparison rather, halfway down, which 7 is halfway. There's 3 items on the left of it, 3 items on the right of it. So 7 is halfway through. It's going to be at index number 3, as you said. And so we're going to compare 5 against 7, and what happens? Five is less than 7, good. And so what do we do? Okay, now the domain that we're looking in is from 0 to 2, indices 0 to 2, right? Okay, we're getting there. So what's our next step? Compare 5 against 2. So now we compare against the center of our remaining part of the list, which is these 3 guys. We compare 5 against 2. Okay, and what do we find? Five is greater than 2. Okay, so what do we do next? Okay, so all that's left is this guy. Our final step, we compare 5 against 5, and what happens? jackpot, we win, right? We found our key. So in that case, the number of steps that's required to find it is 1, 2, 3, 4 steps, 4 comparisons until we find our answer of 5. What do you guys think? It's good? Questions? Okay, so let's try another example. Let's say that we're looking for 31. Okay, so what's our first step? Let me change that. Let me change it to 32, actually. Same idea, though. Okay, 32 is greater than 21. Good. So what do we eliminate and what's left? Okay, we eliminate 0 through 7. And what's left is 26 through 50. Index 8 through 14. Right? So all this stuff is gone, and this is what we're still looking at, right? Okay, what's our next step? What do we compare from the remainder of our list? We look at the center value, and 32 equals 32, so jackpot, we found it, right? So how many steps did this take to find our answer? 2 steps. Excellent. Okay, let's try a similar example. Let's try 33. Right now, 33 is a sample that's not on our list, right? So we're gonna not find it, but we're gonna have to take some steps in order to determine that it can't be found, right? So what's our first step? It's gonna be pretty similar to the last one. What number do we compare against 33? Yep, 21, right? So we compare 21 and 33. 21 is smaller than 33, so we eliminate the left side of the list. What do we do next? Now this is still our remaining chunk here. Okay, we compare 32 against 33 because 32 is halfway down our remaining range, right? Okay, 33 is bigger than 32. So what do we have left now? Okay, so what we have left is 40 through 50. We're looking at the center one, 41, like you said, Nathan, that's right. So we're looking at 41. We compare 33 against 41. What happens? Okay, compare 40 because 41 is bigger than 33. So we eliminate these two. 40 is the only one left. We compare it and it doesn't match. So we're done, right? And we say, oh, well, we can't find it. How many steps did it take to not find it? 4. So it looks like we have something in common here if we're thinking about the greatest number of steps it might take to find our key. Right? It looks like the answer is 4 steps. Why is that? Why is our worst case scenario equal to 4? All right, log of n equals the size plus 1. And say a little bit more about that, David. So you're right, we're going to use the log base 2 function here. But why is that, how is that relevant? Okay, 2 to the worst case, or as we were saying before, 2 to the number of steps, right? 2 to the number of steps equals size plus 1. Okay, and we can actually forget about the plus 1 because this is all, you know, we're forgetting about coefficients, we're forgetting about extra terms. So I'm just going to forget about this, right? Which is to say that the log base 2 of the size equals the number of steps, right? If we sort of reformat this guy, you know, take the log of both sides, right? So we've got the log of the size equals the number of steps. So in summary, we would say for binary search is big O of what? Log of n. Very nice. I'll stick with the n's on here, where n is the size of our list, right? Or you could say big O of log of size or log of x, you know, however you want to say it. But as long as you got the log in here, that's the right idea, right? Questions? What do you guys think? Okay, cool. Let's try another one. So let's move away from searches. Oh, well, maybe I should say one more thing about the searches. Which search is better and why? Yeah, binary search is faster than sequential generally, and it does depend on the input. That's true. So in either case, it's going to depend on n, right? The bigger the list is, the longer sequential search is going to take. The bigger the list is, the longer binary search is going to take. LG is log base 2. Yeah, that's exactly right, David. But binary search is faster, right? Assuming the list is already sorted. That's right, Sean. So if you have to account for the time it takes to sort the list, then maybe sequential search is faster. Because as we're going to see in a second, sorting the list takes quite a bit of time, more time than it takes to search it, right? But assuming that you started off with a sorted list, you would definitely want to use binary search instead of sequential because of the relationship of n versus log of n. What is that relationship? And why would you pick this one over this one? Yes, because that's perfect, Sean. Because for n greater than 1, log of n is less than n, right? When you take the log of a number, it makes it much smaller, right? Which means the length of time that it takes to do your search is smaller, which of course is what you want, right? Instant results, or as fast of results as you can get, right? So, okay, so you would pick this search over this one because this one has a smaller function, a function that grows less quickly than that one, right? Which means it's faster. Okay, cool. So now let's try some sorts. We'll do a couple of sorts and compare those. Yeah. So let's start with bubble sort. Okay, so let's say that I now have an unsorted list, right? So I'll throw a list up here. Let's do 4, 1, 8, 2, 6, 7, 3. Okay, good enough. Okay, so I've got a list. I want to bubble sort it. How does that work? Does anyone remember bubble sort?
So for the bubble sort, that's the one where you compare the first two values, and if they're out of order, you flip them, and then you compare the next two values, and if they're out of order, you flip them. Is that the right one?
Yep, that's right. Perfect. So what would be after? Let's do the first round, right? So 4 and 1 are out of order, so I switch them. Okay, so I put in the 1. Then 4 and 1 have switched. This is happening in place inside the array, right? So now I'm comparing 4 and 8. So what's the next number that I put down? 4, good. Then the 1 and the 4 are in. Now I'm comparing 8 and 2. So what do I put next? 2, good. Then the 8 and 2 have switched. Now the 8's sitting right here. So I'm comparing 8 versus 6. So what's my next value to put in? 6, good. Okay, and then 8 and 7. 7. Lastly, 8 and 3. Bless me. 3. And then that 8 sort of bubbled up to the right-hand side. That's why it's called bubble sort, because it kind of bubbles all the way up to the right. Yeah. Okay, so that's round 1. Okay, what happens next? Do it again, round 2, right? We don't have to do the whole thing, though, on round 2, good point, Sean, because we're guaranteed that the 8 is in the right spot. The largest value always bubbles up as far as it can go to the right. So this 8 is already done, okay? And so I'm not gonna sort this one. I'm only gonna go up to here and then stop. Okay, so what's the first number that I'm gonna get? One, good. Okay, and the worst case is n minus 1 passes. Yeah, so yeah, we'll get to that in just a second, Sean. Yeah, that's right. Next one is 2, good, and then 4, and then 6, and then 7. Oh, 3. Very nice, not 7, 3. Thank you. You said it right. I said it wrong. 3, and then 7, and then 8. Cool. Okay. So now, what do I not have to look at for my next round? What do I know for a fact are in the right place? 7 and 8. Yep, also the 7. So I'm just going to continue sort of like this. Okay, so next round, what do I get? Or if someone wants to give me the whole thing, you can. 1, and then 2. Yep. 4, 3, 6, 7, 8. Nice. On my next round, I don't need to do that one. Right? Okay, so let's do my next round. What have I got here? Yep, next pass gets them in order. So I have 1, 2, 3, 4, 6, 7, 8. And now I'm done. Right? Let me ask you a question. What's the worst case scenario for bubble sort? In what order does the original list need to be in order to require the most steps until I get a sorted list? Yeah, descending order, reverse order. So if I go, 6, oh boy, if I can count backward, 6, 5, 4, 3, 2, 1. Okay. So what's going to happen here is that the 6 is going to bubble up to the right, but the rest of the list is going to remain in reverse order. So my next step will be 5, 4, 3, 2, 1, 6. People see that? Does that make sense? Right, the 6 bubbles up, but the rest of them don't have any opportunity to change place because we're always moving the 6 across every time. Yeah. So what's my next step going to look like? Let's see if you can get the whole thing. Good. 4, 3, 2, 1, 5, 6. And remember, here I'm not looking at that 6. Here I'm not looking at the 5. Okay, what's my next round going to look like? Okay, 3, 2, 1, 4, 5, 6. Very good. Okay, so now I'm not going to do the 4. I know that's in the right place. Then 2, 1, 3, 4, 5, 6. I'm not going to look at the 3. And lastly, in order. 1, 2, 3, 4, 5, 6. Okay. So now that we've done a couple of examples, let's start counting up. Yeah, so that's why I did this sort of worst case scenario, because you have to go all the way through until you stop. In this one, you could stop early, but that depends on how the algorithm is coded, right? Because if you want to stop early, what you need to do is keep track of whether or not you've swapped anything as you go across. And if you do a whole round without ever moving anything, then you could be done. So what you could do in your algorithm is just have a Boolean variable that keeps track of whether or not you've swapped anything. And David, in that way, you can know that you didn't change anything, that you know that it's in order without needing to go through it again. So you can sort of avoid going through it a second time, right? And save that coefficient, that factor of 2, right? Just by keeping track of a Boolean variable and just changing it each time that we swap, right? To say, oh, yep, we swapped, so we may not be in order yet, right? But for this one, we don't need to do that. It's just the worst case, so we need to sort the whole thing through. And what I'd like to do is count up the number of swaps that we're doing. That'll be it. Each step is a comparison, and then possibly a swap. Or maybe I'll just say comparisons rather than swaps. So each time we do a comparison, that's a step, because you have to evaluate an if statement. So that's a step. The computer has to look and see if it's true or false, right? And so how many comparisons are we doing on our first round? N minus 1, right? How about on our second, because we compare these two. So 1, 2, 3, 4, 5. So n comparisons there. On the next one, we have 1, 2, 3, 4. We don't have to do the 6. So this would be n minus 2, right? Next one. What would the next round be? N minus 1, n minus 2. Almost. You're almost there, Sean. But let's do the rest of it, and then I think it'll be a little bit easier to see. Yeah, almost. Okay, so n minus 3, right? N minus 3. So next one will be n minus 4, then n minus 5, right? So if we were to actually put the numbers on here, we'd have 5, 4, 3, 2, 1, right? Those would be the actual numbers. And of course, we want to add them. So sum is the right answer here, because how many comparisons did we do total? Well, we add up all the ones that we did on the different rounds, right? So now if I have 5, 4, 3, 2, 1, well, then my total number of steps is going to be the sum from I equals 1 to what? N minus 1, very nice, of what goes in here, n minus I, or to make it a little easier, I, right? Just going in reverse order. I mean, it comes out the same way, right? But this will work as well. And what is the sum from 1 to n minus 1 of I? Close, David. Not perfect, but you're almost there. Nope, not quite. There we go, Sean. You got it. N times n minus 1 over 2. Let's check that and make sure we didn't screw it up. Right? So what we're supposed to get here is n equals 6, right? We've got a length 6 list. And so I should get 6 times 5 is 30 over 2 is 15, right? And 15, 5 plus 4 is 9, plus 3 is 12, 14, 15. So that is correct. So I think, David, you're thinking about the sum from 1 to n. That would be n times n plus 1 instead, right? But this one's n times n minus 1, which, you know, close enough. It actually doesn't matter. Yeah, you misremembered. That's fine. No big deal. It actually turns out to not matter because this is going to be equal to what? Well, this is going to be equal to n squared over 2 minus n over 2, if I just multiply this out, right? Which means for big O, it's big O of what? N squared. Very nice. Because whenever we do big O, remember the coefficients, like this guy, don't matter, and the smaller terms don't matter. The only thing that matters is the largest sort of variable to a power in the largest term without the coefficient. So bubble sort is big O of n squared. What do you guys think? Good? The average case behavior is better. Better than what? Better than the worst case? Better than sequential search? So I would say, yeah, this is sorting. That's right. Yep. So yeah, so it is, I would say it is worse than sequential search, even on average. Certainly the worst case is worse, but I think the average case is also going to be worse. Because up here, the average case for sequential search would be n over 2, because on average, you'll find it halfway down, right? Versus here, I think the average case is going to be definitely like you know, an n squared sort of situation. You might have a better coefficient on here, but you know, but I think that bubble sort is still going to take quite a bit longer. Okay, so let's try another one. All right, so let's try. So to do bubble sort and then binary search is worse than a sequential search. Yes, if you're only doing one search, right? Because if you're only doing one, then you would have sequential search, which is n squared, plus binary search, which is log n. And n squared plus log n is way more than just n by itself for a. But if you do a bunch of searches, it's cheaper. That's exactly right. And you could wonder, hey, how many searches do I have to do until it makes more sense to sort it first? That's a totally a fair question, right? I'll leave that for you guys to think about, right? It does depend on the size of the list. That's true. It depends on the size of the list and on how many searches you want to do. Actually, it depends on the comparison between the size of the list versus how many comparisons you want to do, how many searches you want to do, pardon me. Right, so I'll let you guys sort of figure it. That's a cute little problem. I'll let you guys figure that out. Okay, so I was going to do selection sort next, but we're kind of running low on time here. Does anyone remember how long selection sort takes instead of bubble sort? So let me help here. So remember, selection sort is the one where you switch out the smallest one on the list with the leftmost one on the list. You remember that? So you look through the whole list, find the minimum, and then you swap that with the one that's all the way on the left. And then you do it again, right? That's one round. And then you repeat that over and over for as many items as you have on the list. Does that ring any bells? Selection sort? Yes, no, silence here, over here. It is the same complexity as bubble sort. Yep. Yes. So it's the opposite in terms of function in a certain way. It's close, yeah, sort of the opposite. I agree with that. And since it's the opposite, it takes the same amount of time. Yep. So Lucas and David, you had exactly the right idea. It actually is also an n squared, big O of n squared, because it works in a similar kind of way, right? So let me ask you this. We've got bubble sort, which is big O of n squared. We got selection sort, which is big O of n squared. Is there a sort that's faster than either of those? Is there a better sort? Merge sort, that's a good one. How long does merge sort take? Radix sort, that's another one. Yeah, how long does that one take? Does anyone know the run times of those algorithms? Yep, that's right, Sean. Yeah, it's n log n for merge. That's right. Great. Radix sort? Yeah, just log n, but there's some interesting caveats. Sort of like binary search, you have to have the list sorted first. There's some interesting caveats to radix sort. So it is fast, but there's some little details that you do need to worry about. Merge sort works in all cases. So merge sort, I would say, is a good general purpose sort because it's as fast as you can go. Yeah, exactly. Yeah, so that's right, Sean. So yeah, radix does have that caveat. Merge sort does not. So merge sort is pretty much as fast as you can go without having any weird requirements on your list structure before you start, right? The trick for radix sort is to randomize the list before you sort it. And it turns out you can randomize the list quite quickly, right? So radix sort does sort of beat it if you randomize your list first. But then you have to write additional code to randomize your list in a clever way, because randomizing a list is a whole other algorithm that has its own calculation of its big O as well, right? So you would have to have your list randomization algorithm be very quick, in addition to using that radix sort afterward. If that does that all sort of make sense? You start to see how the game is played here. You have all these different operations, these different functions you can do, right? But then you have to do some functions before you can do other ones in some cases. So then you have to add together their big O notation to figure out the actual total, right? So it's kind of a little game you have to play. Okay, and Lucas, you said, so good average case and bad worst case. Yeah, that's right, Lucas. Yep, exactly. And a lot of algorithms have that property. So hash table lookups have that property, where the average case is quite good, but the worst case is really bad. So it's just a matter of dealing with those little caveats to make sure that your algorithm doesn't die. No, linear is not bad. Linear is great. If you're doing something linear, then you're in good shape for any algorithm. Linear is great, and if you're doing a log algorithm, that's awesome. No, the worst case for hash maps is not linear. I believe it's quadratic, but it's almost always linear. But then sometimes it's quadratic, as I recall. But maybe it's. I would have to look. I don't remember. I haven't done hash tables since I was in school, so I don't recall. No, maybe you're right. Maybe it's constant average case and then worst case linear. No, I think you're right, Lucas. No, that's right. And so, right, yeah, that's correct, because you're using a linked list and you have to search down the whole list for it, which takes linear in the size of the list. No, so you're right, Lucas. So that's another good example. It's not linear versus quadratic, it's constant versus linear, which is still a huge difference, right? So it's another one of those examples where the structure, the structure of your data has really important consequences for the big O of your algorithm that you're going to use. And while we're on the topic, I should probably mention one more. If you're talking about binary search trees, there's a whole study of binary search trees and how long that takes to do, right? So let's go down that road for a minute. I think that'll be a good thing to do. Maybe we'll do that and then we'll talk about the determinant. We'll call it a day. So in the case of a binary search tree, what's the big O for finding an item in the tree? Just a general search. Log n, right? So there's a condition on that though. There's a caveat. So what's the caveat on having your search in a binary tree, which maybe I should draw a little picture here while you write. So I have a binary tree here. Right? So here I've got all of these items, which would be 16, 8, 4, 2, and 1. So 31 is my number of items, and to find an item is 1, 2, 3, 4 steps, right? In the worst case, because the worst case is your item is down at a leaf that you're looking for, right? So you have to start at the root, search downward until you hit a leaf, right? And so this is a big O of log of n, because the number of levels in your tree is the log of the number of total items minus 1. And again, we're forgetting about minus ones and stuff like that when we do big O notation, right? But this data structure has a caveat to it where you're not necessarily going to get big O of log n. That's only for balanced trees. Excellent. What if you had a tree that looked like this, where you had only left children, and all 31 of them are arranged as left children? This is the most balanced tree. This is the most unbalanced tree. And what's the big O notation for search here with an unbalanced tree? The height, good, which is in terms of our number of elements here, which is n, very good. So on a tree, on a binary search tree, depending upon how balanced it is, your search time is going to be somewhere between logarithmic and linear, right? And so obviously you want this one because it's faster instead of this one. So how do you do that? How do you guarantee that you're going to have a logarithmic search instead of a linear search? Any ideas? It does depend on the input. Good. What about it? Depends on, for the input, I assume you mean how you build the tree, right? There are self-balancing trees, that's true. So instead, so I was just doing a general purpose binary search tree, right? There's red, black trees and 2, 3, 4 trees, and those are called self-balancing trees. So you don't have to worry about it, or an AVL tree. That's right. But if you have just a regular old binary search tree, how do you make sure that your tree is balanced like this instead of this sort of accidental linked list that you get out over here with the unbalanced tree? Maybe we should get into the details of why it would be, yeah, we shouldn't sort the input, or let me rephrase that, Nathan. You should unsort the input. It's not that you shouldn't sort it. You definitely shouldn't sort it, but also you should unsort it. And what's the word for unsort? Well, randomize, right? Because what's gonna create this problem, right? Well, if you put in the biggest thing on your list first, let's say that you're building a tree and you add the number 10, right? And then you want to add the number 7. Well, that's going to go on the left. And then you want to add the number 6. Well, that's going to go on the left. And then you add the number 4. That's going to go on the left, right? And if you keep adding these numbers in decreasing order, it's going to make this very unbalanced tree. So if you could randomize your list before adding the items to the tree to build it, right? And they're all random, then that's going to come out with a very balanced tree, rather than if you add the items in reverse order or in sorted. Either way, this is if you add them in reverse order. If you add them in sorted order, then you would put in 1, 2, 3, 4, 5, and they just make a linked list going down the right side instead of the left side, right? It's sort of like sorting, because the best case scenario is your data starts with the middle value, and the next values are the other middlemost values, and so on. Yeah, so that is the best case. But if you randomize it, it turns out that that gives you a very balanced tree as well, right? Because the likelihood that you're going to get something toward the middle after you've randomized is very high, right? Think about it combinatorically, right? What are the odds that you're going to get something near the middle if you've randomized, the list before you start? Does that make sense? Yeah, cool. So we've talked about it twice, so maybe we should just look it up, right? What do you think is the big O for list randomization, right? What do you think is the best worst case scenario, right? So there are lots of ways to randomize a list, okay? But the best one, right? The lowest big O for list randomization. What do people, you think it's n log n? Sean, that's your guess? Anyone else have any guesses? Yeah, that's a good guess. I would guess linear, personally. I don't remember. I've learned it once before, but I forgot. I haven't talked about it in years. I would guess linear. I don't know. Do other people have thoughts?
So just to explain my guess a little bit,
Yeah, please.
when you're randomizing, you're going to have to step through the list to some value, and then you're putting it at like the front of the new list, and then you're going to have to step through the old list again and put some random value second, and so on and so on. But each time you do that, you can keep track of like the values you visit. You're decreasing the length of one list and increasing the length of the other, but you don't have to step through the entire thing of the other if you just keep a pointer to the end or something. And so it's kind of like doing the bubble sort, where you're eliminating some of the list as you go through.
Right. The list does shrink as you're moving them across. That's true.
Yeah, which is why I think n log n, but I don't actually know.
Okay. And then David, your idea is we use random swaps of indices, right? So I guess David, with your idea, we would pick two random numbers between 1 and the list length, and then swap the indices at that value and just do that n times, and we would come out with a randomized list. Is that your idea, David? Which is very different than Sean's idea, right? So, and obviously things can be more or less randomized. So depending on your algorithm, maybe you're going to come out with a very random list or only kind of a random list, depending on your, how good your algorithm is. So let's take a look. Let's try list randomization algorithm. Fisher-Yates shuffle. Yep, that's the right one. Okay, so here's your shuffle. Boop, boop, boop. Okay, from 1 to 9, you rolled a 2, so you swap 9 and 2. Then from 1 to 8, you rolled a 8, pass. 1 to 7, rolled a 4. So it looks like what you're doing is a little bit like bubble sort, where it's moving across here. And what you're doing is picking a random number from 1 up till the remaining part of the list, right? And it looks like this is linear. Right? Yeah, do the shuffle, right? Yeah, exactly. Let's see the modern algorithm. Let's see here. Yep, reduces the time complexity to linear instead of squared. Okay, and here's the algorithm in pseudocode for I is from n-1 down to 1. Pick j, which is a random integer from 0 to I, our for loop index, and then exchange AJ and AI. Cool. Okay, so it is linear. Getting the random integer costs something. Yes. So that absolutely. So you have to be worried about how long this takes, right? Right. So let's look at that, right? So this now we're playing the game, and that's a good way to end it. Let's play the game to end it, right? Let's do RNG runtime. Oh, I should have Googled that. This is not the right thing. Okay, let's try a different one. Multiplication and modulus. How about this? Big O. Boo. This is. Oh wait, that's the question. N times the sum of the natural log of I over I. So the total average complexity is theta, which we now know what that means, right? So it is bounded above and below by n times the natural log of n squared, right? Okay, so n log n squared, which means that if you're putting that into our last guy here, okay, so then you would have n times n log n squared, where your n is decreasing, right? As you go, as I decreases, right? Because you're going I from n minus 1 down to 1. So your n there would be decreasing. So this wouldn't actually be linear if you include the randomization time, right? Yeah, and it would have a log squared factor in there actually, but that would all be decreasing as I goes down, right? But that's true, Lucas. That's only if you want it to be very uniform. So the random number generator that we found was a really nice one, right? That was like an ideal one, I think was the word that they used. But you could just start with a random number, add another random number to it over and over, and take modulus as you add those numbers on, right? But if you're okay with a bit of non-uniform, it's pretty much free, right? Well, now just to play devil's advocate for a second, Lucas, when you're adding numbers together, that's not free. It is constant, but it's not free, right? So if this was a constant process, which I guess I should mention really quickly, right? There's this sort of hierarchy of how good you can get your algorithm to be. You can be big O of n squared. Faster than that is linear, big O of n. Faster than that is logarithmic, big O of log n. Faster than that is constant, which is big O of 1 is the way that that's described. And that means you can do the thing in an amount of time that is not dependent on anything, right? It just takes this much time, period, right? You don't have to worry about the length of your list or how the size of the set of random numbers you're trying to do or anything like that, right? And to be clear, adding numbers together on your computer is not constant. It does depend on how big your numbers are. Because of course, adding numbers together will take more time the bigger the numbers are. You know that from third grade, right? When you're adding numbers together, it takes longer to add together 3-digit numbers than 2-digit numbers, right? And of course, the computer has the same issue. So now, rather than looking at this sort of fancy randomization, we looked at, Lucas's idea, which is not quite as accurate, but much faster, right? But it's not perfectly constant because the bigger the numbers are, the longer it takes to add them. Well, that depends on how many digits there are and how many processors you have, right? So again, you're not wrong, Lucas. You're 95% right. I'm playing devil's advocate, right? So you're almost completely right, but it does depend on what you're adding. In this particular situation, if we're trying to put things on a binary search tree, which is where we got to this whole mess, right? Are you going to be putting trillions of things on a binary search tree? Or, are you going to be putting, 10 to the 100th power things on a binary search tree? No, well, no, you're not, right? Because that would be stupid. And it would have to be that big in order for you to really care about how long the addition takes, right? And with floats, yeah, maybe, sure, okay. But what I'm saying is, in order to care about how long the addition takes, you would have to be adding numbers that have, thousands or millions of digits in it. But millions of digits in a number, that's 10 to the millionth power, different numbers that you would want to be putting into a binary tree. Like that doesn't make any sense. Why you would never do that, right? So at some point the game falls off because you don't need to worry about the time complexity of adding numbers on your computer, because you're never going to be adding that big of numbers for most of the time. Yeah. So Sean, yeah, 10 to the million is not a viable number for anything except some weird stuff in pure mathematics. Certainly nothing physical that ever happens. The number of atoms in the universe is like 10 to 100, right? 10 to the million is not a viable number for pretty much anything except for some really weird proofs. So, all right, and I'm over time, so I should stop it there. Hopefully this was enlightening for your web work. And I can go over the proofs on Wednesday. If people have questions on the proofs for this week, happy to talk about that on Wednesday before we jump into chapter 12. And other than that, I think that's all I've got for you for today. So let me stop the recording here.